As you can see, we have 4 channels. We have power and control interfaces around all of those 4 channels. If I turn the unit around, then we can see on the back we have USB and LAN interfaces, and we have 12 volt DC input for power. Coming back round to the front, over here it says that this is a 5 GHz oscilloscope and that it is a 12-bit product, 12-bit ADCs. It also says that it's an SX RTO. Look around, what have we got here? We've got, first of all, the channel controls with their status displayed here, and above we have a complete summary, tabulated summary of the scalings and offsets of the channels and of the time-based control. Up here at the top, at top of the screen, we can see a summary of time-based settings. We're operating in real-time sampling mode, and you can see here are the waveforms being captured at quite a fast rate. Over here we have trigger, and in the trigger summary we've got a rather useful frequency counter here. This is indicating the trigger rate, the incoming trigger rate, which happens to be at the moment on channel 1. Looking slightly to the left here, these are a summary of the channels, again their scalings and their offset. If I turn off a couple of channels, you can see that I continue to get an indication of the waveform on those channels up in the status summary at the top here. Now that might be important because those waveforms might, for instance, be contributing to a maths waveform that we are displaying. Let's turn channel 1 back on and let's call up the display menu, and we will select dual graticule instead of 4. Let me call up another menu as well. I'm going to call up the acquire menu, and as you can see I've got the versatility here to put up 2 menus up at the same time. This allows me to configure from the main menu controls at the bottom of the screen here. I can call up all the menus that I want for a particular application. The user interface is, if you like, user configurable. The screen is touch operable, so we can change our trigger channel. We can grab hold of the trigger level here, move it up and down. We can see the parameter control enlarged here. I can move trigger level using this control as well. Now, at this point, I've come to the end of our real-time sampling range. We're now sampling at 500 megasamples per second. I've only got 50 samples across the screen, and my waveform isn't exactly full of detail. This is not a problem because the waveforms I have here are repetitive, so I can switch to random ETS, random equivalent time sampling, and my detail in waveform is fully restored. I can also at this point push up record length. Now running at 200 gigasamples per second and 20 kilosamples, 20,000 samples across the screen. Let's get some measurements on. With statistics, I want on channel 1, I want rise time, I want amplitude, peak to peak jitter and RMS jitter. And you may notice that as I've gone through the process of turning those measurements on, I've been getting an indication on the screen as to how those measurements have being made. Here, for instance, the RMS measurement is being made at this point across that particular trace width. Let's get us up to 2 nanoseconds per division. So now I'm running at 1 terasample per second, still 20,000 samples across the screen. And we can see that we have a positive RMS jitter of around 1.2 picosecond. So this is a very, very low jitter oscilloscope. We have 5 picoseconds peak to peak. We have 64 picoseconds of rise time on channel 1. That is coming out at a mean at the moment of 65.74 picoseconds. Well, a 5 gigahertz scope should have a rise time of around 70 picoseconds. So clearly, given that we're measuring the rise time of the scope and the rise time of the pulse generator there, we've got plenty of bandwidth to reveal our rise time. If we take a look at a block diagram of the signal path in our SX-RTO, and if we color the various elements on that path according to their relative cost, what we see is that the 5 gigahertz track and holds are relatively expensive. The rest either moderately expensive or relatively low cost for every function within the product. If we contrast that with the block diagram of the signal path of a typical 5 gigahertz real-time oscilloscope, first of all we'd see that behind the track and hold we would now have 10 to 40 gigasample per second A to D converters, more likely to be 8-bit or 10-bit rather than 12. But these are significantly expensive components. The very high data bandwidth that they produce has to be handled by really high-speed data path and high-speed memory. And that can be tremendously expensive. Hence the very red block in the top right there. And to that we must add switched gain amplifiers just before the track and holds and the trigger pick-offs. Those in themselves are relatively high cost. So overall the real-time oscilloscope package is quite significantly more expensive than the SX-RTO. Of course it is those 20 gigasample per second A to Ds that give the RTO a much higher speed or single event capture capability. However, those relatively high speed A to D converters and the very expensive memory bandwidth still doesn't get us all that we might need in a real-time oscilloscope. If we consider the narrowest pulse that a 5 gigahertz oscilloscope would be able to capture, that would be a 150 picosecond pulse or data interval. If we capture that at 20 gigasamples per second, we're just going to get 3 samples within that pulse, and the fidelity of its reproduction is rather lacking. Now in real-time mode, our sampler extended real-time oscilloscope will do a rather worse job. In this case we really don't have enough samples to capture that 150 picosecond pulse or data bit in single shot at all. We can capture slower transient events, but we will miss that 150 picosecond pulse. All broadband real-time oscilloscopes and the SX-RTO use random equivalent time sampling on repetitive waveforms or clock-related data eyes to increase the sampling density. So, the SX-RTO gives us a new affordable price point for the broadband oscilloscope. Our high-speed signals do need to be repetitive rather than transient, but when they are, the SX-RTO will resolve high bandwidth signals with 12-bit and 1 picosecond sample resolution. That's 150 samples in our example pulse. So that was the PicoScope 9404 SX-RTO, our sampler extended real-time oscilloscope.